It's for you.
Hello, Werner.
Who are you?
I am the architect. I've brought you here to see this, my system.
What? That? Is that a Perl script?
Listen, Werner, there's a problem with the system. Ergo, I've brought you here. It's glorious in almost every single way. Every single one of them are my babies. I've even named them. However, every time I add a new service, I have to build a new rack. Ergo, it's becoming very expensive. Also, it's very hot in here.
Have you considered cloud migration?
Cloud migration?
I think we need a montage. No servers. More. Do it again. One more time. Come on.
Wait, so you're saying I can scan my container images straight from my CI/CD pipeline? Yes!
Look, you need to build with cost in mind from the outset. You need to be a frugal architect.
The frugal architect. Oh, Werner, wait!
What?
Can I get some free credits?
No.
Please welcome the Vice President and CTO of Amazon.com, Dr. Werner Vogels.
Wow, I'm absolutely blown away. This is day 4. You're supposed to be in bed. Yeah? And really, absolutely, I'm totally humbled by the fact that, I arrived here at 6 a.m. this morning and you guys were really standing in line. I don't deserve that. Absolutely. What do deserve an applause, by the way, is the quartet that just played. So can I get your hands again? Some other people that actually need you to give some applause. Can I get the heroes to stand up on front line? These are invaluable members of our community. They make it what this whole community makes so special, and hopefully also why you're all in this room today. And especially want to shout out to Luke, who got the Now Go Build Award this time around. Okay, thank you. I know you probably all cringed a little bit when I said cloud migration. Yeah, after all, I actually noticed that for quite a few of the people in the room, you've grown up your career in cloud. For you, there was no pre-cloud, no hardware, no constraints like that. And, but, you know, the great thing about sort of moving out of that whole hardware environment into the cloud was that we suddenly could build these architectures that we always wanted to build. Yeah, we no longer were constrained by, you know, the physicality of all those servers. And also I could actually, as a distributed systems guy, to actually start talking to my customers about how to really build reliable, big-scale systems. And, but, you know, there was something about that old world. If you get as old as me, then you start seeing the past with a little bit of rose-colored glasses. Yeah. There were things in the past, actually, in this world that had these hardware constraints that actually drove a lot of creativity. Yeah, if I think about, and I'm going to talk a bit about the cost of all of those all the systems that we're building. And I'm going to drive that by actually my experiences as the CEO of Amazon for the past 20 years, almost. Yeah. And if I think back about being the pre-cloud days of Amazon, the retailer, we were really good at predicting sort of how much capacity we needed. We could sort of have made then the decision to make sure we had 15% hardware over the expected peak for that year. But still, nothing could happen to us, nothing unexpected. Now, I remember at one day, in the days that Wii's and PS4s were very scarce, someone posted a message somewhere saying, tomorrow Amazon will have 1,000 Wii's for sale at 11 o'clock in the morning. Well, you know what happens at 5 minutes to 11, eh? F5, 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 assuming you're a Windows user. Yeah? And so traffic explodes. And absolutely, you really had to, we worked our way around it, and we were very creative in trying to solve the problem to make sure that all the other customers still could be served. But still, you know, it required a lot of work and a lot of hand-holding. But more importantly, there were also restrictions on business innovation because of that. Because it's a few weeks before Black Friday, a team would come to me and say, oh, we have this brilliant idea to do X, Y, or Z, and it will give us, what is it, additional revenue at this much. You would scratch your head and think, like, how are we going to do this? But we always made it work. There was sort of an art in sort of building these systems and living within the constraints that you had. Now, cloud, of course, removed all of those constraints. Now, suddenly, you were no longer stuck. You could do all these things. I didn't have to have long conversations with the business about sort of reducing their footprint or things like that. You could do everything. And as always, when constraints get removed, when we throw off the shackles of something that keeps us down, we have a tendency to swing this pendulum all the way to the other side. Suddenly, what is the most important thing is actually to move fast, to get new products out, to start thinking about all the things you could do now that you couldn't do before. Yeah, and that's amazing. And we have seen amazing innovations in the past 15 years happening on top of AWS. But if speed of execution becomes more important, we kind of lost this art of architecting for cost and keeping cost in mind. And if this is your 12th reInvent, just like it is for me, you may go back to this first reInvent in 2011. And I put up these sort of, I think there were 12 sort of tenets that I thought you should think about when you were building for the cloud. Yeah, and one of them was to architect with cost in mind. Because suddenly you could. Yeah, remember, we're making cost explicit for all the resources that have been used. And so it was very, very easy for you to start thinking about what is actually the cost of this system that I'm building right now compared to the other one that I built yesterday. And so if you no longer have these constraints, it drove amazing innovation. But the macroeconomic climate sometimes changes, and more noticeable the last few years is that companies more and more have become interested in sort of what is this all costing me? And so I hope that today, you know, you're going to listen a little bit to me about my experiences of the past 20 years of building cost-aware architectures. And by the way, you've already seen amazing innovations and announcements this week. This is not going to be one of those keynotes. So sit back, take out your notepad, and start making notes today. And so many of us don't have to live within these constraints anymore, but there's quite a few companies that actually do. And a great example of that is the public broadcasting service. You all know that, they make all these programs for their affiliates, and their famous tagline is, of course, supported by viewers like you and me. But they have to live within a strict budget. And so it's not only that they provide all these programs for the affiliates, they also stream all content. And at the 40th anniversary of Sesame Street, they completely broke down because they were streaming out of their own data centers. This is 2009. And they knew that they couldn't continue to do this because they just couldn't afford the hardware to do this at massive scale. So they migrated over to AWS. And as always, if you just do lift and shift of something that wasn't scalable and efficient in your own data center, it isn't suddenly scalable and efficient in the cloud either. But they wanted to continue to start off with, at least with the existing software, and so they made use of OpsWorks and time-based scaling. That basically meant that they were still not very resource efficient, which is crucial for them, because the money they can save, they can do a lot of other things with. And so while they actually moved to the cloud, they also started to realize that they had to re-architect. And they re-architected using every possible AWS service that they could. And so they were streaming directly out of S3 and out of CloudFront. They moved over to ECS and Fargate, really absolutely driving all of their costs down. They actually reduced the streaming cost by 80%. And if you were a fan of the Ken Burns documentaries, just like I am, they recently had this documentary called The American Buffalo, extremely popular, and a great documentary. And it went off without a hitch at 80% less than 80% cost savings at the same time. Not only because they moved to the cloud, but because they re-architected for the cloud with cost in mind. Now, next to cost, there is something else that is really on my mind these days, and it should be on your mind as well. This is a freight train that is coming your way, and you cannot escape it. I think, in absence of us providing you with sort of the information about milligrams CO2 used by your services, cost is a pretty good approximation for sustainability. And we've got quite a few companies that are asking us to really help them build more sustainable architectures. And I think us as a society, as tech society, as technologists, have a major role to play in making sure that our systems are as sustainable as we can be. And remember, in AWS, you pay for each individual resource users, which means that cost is a pretty good approximation for the resources that you've used, and as such, your contribution to sustainability. Now, throughout this talk, when I say cost, I hope you also keep in mind sustainability at the same time. Now, a company that is actually the lighthouse in this is one of our oldest European customers, WeTransfer. And I don't know if you know them, they actually support having these very large files that you can upload and then distribute. They reorganized themselves as what's called a certified B Corp, a company that has the highest standards in environmental, social, and fiscal transparency. And they are still able to innovate while actually lowering their emissions at the same time. And their server usage was their biggest energy dependency, and they re-architected in such a way so that they could start to forecast, track, and measure carbon emissions while serving 80 million people a month. And they've done this for some very unique strategies. And you'll see some of these strategies coming back into my experiences as well. Now, if you look at the video before that, I presented the architect with the frugal architect. And basically, this is sort of a book where I've sort of encoded my experiences of the past 20 years of building cost-aware, sustainable architectures. And I think, as builders, we really need to start thinking about this. Not only because we want to be frugal in the way that we use our resources, but also as sustainable as possible. Now, these are not hard rules. And I call them laws, but they're not like legal laws. They're more like bio and physical laws, where you have lots of observations and then you codify those in a framework. Of course, nature doesn't care about those laws. The laws are for us, such that we have a framework to think in. And those are not hard rules. Yeah, but to actually give it a little bit of structure, I've put them in 3 different categories. One of them is design, measure, and optimize. And I want to start off with probably what's the most important thing. Yeah, and the most important thing here is that cost needs to be a non-functional requirement. And if you think about non-functional requirements, there's all these sort of classical ones. Security, compliance, performance, availability, all of these are actually things that are not the specific features and functions of the application that you're building, but the ones that you have to keep in mind at all times. Yeah? I think security, compliance, and accessibility are non-negotiable. Yeah? The other ones, you can make all sorts of trade-offs on. There's actually 2 other ones that I believe should be in this list as well. Cost and sustainability. Both of them should be treated at equal weight when it comes to non-functional requirements for your business. Now, it is easier these days to measure cost. Now, if I go back to my early days as CTO of Amazon, I basically had to write a big check up front to this database company before I could start using their architecture. And it wasn't just a little check, it was a big check, because I needed to think 5 years ahead. How much capacity do I think I have 5 years ahead? Because that was the only way to drive costs down. And so it was very hard on day 1 or on the second year or the third year to think about how much of that cost is actually going into the systems that I'm building at this moment. In AWS, of course, that's radically different. Yeah? There, pay-as-you-go goes for each of the resources. And actually, when we started building S3 as being the first really big AWS service, we had to think about what kind of resources are we using, what is our cost that we need to expose to our customers. Because we want our pricing model to be cost-following. Cost-following means that we expose our costs to you. Now, we sat around the table and we were thinking, well, what are the 2 biggest costs that we are going to have in this that we need to put in the pricing model? Transfer, of course, bytes on the wire, and bytes stored. But when we started onboarding our very first customers, we started to realize that there were more resources being used by them. And we actually needed to add a 3rd dimension to how we would price this service. And that 3rd dimension was the number of requests. Yeah? What I want you to take away from this is that, especially if you build something radically new, you may not have an idea about exactly how your customers are going to use your system and how much resources they're going to use for each operation. So make sure you can observe that and immediately react to it so that you understand exactly the kind of resources that you are using to serve your customers. By the time we built DynamoDB, we had this completely down to an art. And if you remember, when we launched DynamoDB, we launched with 2 types of reads. One read was eventually consistent. Basically, it runs a quorum underneath there. Let's say there's 3 nodes in the quorum. It goes down, does 1 read to a node, and you may get the last update or not. We also launched with a strongly consistent read. The strongly consistent read basically went under the covers, did 2 reads towards the quorums to make sure that you would get the latest update back. You have to do 2 reads for that. So we made sure that eventually consistent was half the price of strongly consistent. Because we had to do twice as much as work in strongly consistent versus the 1 read for eventually consistent. So I want you to take away from that, you have to consider cost at every step of your design to really keep that in mind. And then if you think about sort of your business, because after all, we're not just building technology for technology's sake. We're building technology to support our business. And I hope that all of you are in an organization that probably has some sort of agile development strategy where you are close with your business partners. We continuously talk about the functionality of things. How reliable does it need to be? How scalable does it need to be? And most importantly, how much will this cost? And that's a conversation we haven't always had. But we need to have this conversation continuously with our business partners. Now, at one moment, especially when I started advising more and more startups, I tried to hammer this down on day one when a startup is thinking about their product. What is the revenue model that you think you're going to have? How are you going to make your money? And then make sure that you build architectures that follow this money. That's important. Because if your costs rise over a completely different dimension, you're going to be toast eventually. Yeah, so align cost with revenue. Now, if you think about a company like Amazon.com, probably the best measurement for our success of the operations is sort of orders a minute. Yeah, that's basically sort of the dimension where we are making revenue over. What we then need to make sure that our infrastructure scales in such a way that actually cost doesn't grow in a completely different dimension, but also that we can use economies of scale eventually to drive our costs down further. And as you can see, sort of if the difference between cost and revenue would be profit, profit should increase over time if your cost rise over the same dimension as that your revenue is. I've also worked with younger businesses in which it didn't go that well. This particular one was actually one of the first ones that were building these MiFi devices. This was before ubiquitous mobile communication. And so, basically you had to buy a 10 gig data package every time when you ran out. And it's a good model. They basically were running over one of the bigger telco providers who they had to pay. So every time, basically, if you look at the one on the left, basically the green boxes are actually unused capacity that they just had part of their revenue. And then customers came to them and said, you know what, all this buying every time 10 gig, so bothersome, can't we have an unlimited plan? And without thinking, probably really thinking, the company said, yes, of course we can. And then, it put a decent high price against it. And what happens then, if you remove constraints, suddenly customers start behaving in ways that you didn't anticipate. They started watching Netflix over their mobile device. Yeah? And it's pretty quickly, actually, the usage ramped up tremendously in ways that customers were no longer paying for it. The company went out of business because of this. Yeah? Be really smart to make sure that the dimensions over which you make revenue are also aligned with where your costs are coming from. Now, it's always good to think about flywheels, and you probably have seen this napkin drawn by Jeff Bezos many times. Now, flywheels are things that sort of continue to put energy into it. The more energy you put into it, the better it works. So it starts off with selection. And selection means the number of products in the catalog. The higher the number of products in the catalog, the higher the likelihood is customers can find what they're looking for, gets a great customer experience, drives more traffic to the site, makes that more sellers want to sell on the site because there's more traffic, which means that the catalog gets bigger, more products in the catalog, selection grows. So you get this continuous cycle that suddenly starts to accelerate and drive growth. And then if you make use of that, the economies of scale of that, to lower your cost structure and then lowering pricing for your customers, you have another flywheel that drives into that. Suddenly, two things happen going to that customer experience. And it really accelerates the way your business grows. So really, make sure that your business decisions and your technology decisions are in harmony with each other. Now, and sometimes it's easy to think up front. These are the resources I'm going to use. This is sort of what I need in my pricing model. When we started Lambda, that was a whole different ball game. Yeah? Again, we knew that customers wanted to have serverless compute, just like serverless storage and serverless databases. They didn't want to think about scale and reliability and things like that. It just needed to work. And we knew customers wanted that. We also knew that we wanted to make the principled decision that we should be charging over 2 dimensions, which would be, milliseconds of CPU used and amount of memory used over a certain period. Now, as always, we didn't read, if you build something radically new like Lambda, you have no idea how your customers are actually really going to use it. That was what we learned from S3. Yeah? So we also knew we needed to get insight in this before we could build the right architecture. We didn't have the right architecture underneath that we could build Lambda on. So fine-grained isolation and hotspot management and things like that. So there was this tension between these 3 different things. Yeah? The 3 different non-functional requirements. Security, strong isolation, cost, and getting insight into your customers. So we made a decision up front, given that we didn't have the technology to make this very cost effective, to actually sort of sacrifice immediately cost. So we did 2 projects. One was basically starting Lambda, and the second, completely greenfield projects underneath to start to figure out what kind of infrastructure we would need to support this. So we were willing to take out technical and economic debt on day 1. We also knew immediately on day 1 that we had to pay that off eventually. Because just like any other debt, the interest keeps compounding. And at some moment, it becomes unattainable. So we started off with to build Lambda, we started off with the smallest building blocks we have that could give isolation. And so those were the T2s, the T2 instances. And you probably all know about virtualization by now. Basically, T2s run on top of a hypervisor, runs on real hardware. And these are actually pretty coarse-grained. If you think about Lambda functions being really small, these T2s, even though they're the smallest instance type that we have, is much bigger than what we needed to actually execute that function. But we needed the isolation. We needed the security isolation. So we went ahead and actually implemented using T2s. Yeah, so basically, you had a whole compute pool full of T2s where we were executing these Lambdas in. And we made sure that each Lambda from each account would be executed inside isolation, so inside the T2. Now, you can already see what's happening there is that some of these T2s are tremendously underutilized. Why? Because there's only 2 or 3 of these Lambda functions executing every second. But also, we saw exactly the other side happening. Because quite a few of these Lambda functions actually happened in synchrony. So you would get not 1 execution of this Lambda function, you would get 1,000 or 10,000 at the same time. And so where on one hand they were underutilized, quite a few others were completely overloaded. And we couldn't do fine-grained resource management because we didn't have the fine-grained capabilities underneath them. So we knew we had to repay this debt. And we did that by doing massive innovation. And the innovation became what we now know as Firecracker. The idea of building micro-VMs based on KVM. And we could launch a full isolation virtual machine in a fraction of the time that it would take to spin up a T2. And KVM exploits hardware virtualization, so that makes it that it's extremely efficient for these very small VMs that we're doing. And so also, it allowed us, given that now we have a very small boundary in isolation, to make sure that we can use multi-tenancy. That it's very easy to do hotspot management now because you have these very fine-grained isolation boundaries. And we could make sure that we could fully optimize memory and compute by basically hotspot managing over different types of physical hardware. And so all of this drove tremendous innovation. It's not only that we were able to move our customers from the T2 environment, Lambda, without them noticing, over to Firecracker. Well, to be honest, they did notice. Everything became a lot faster. And their performance became a lot more predictable. But we didn't tell them that. They were just happy with that. But it also gave us an environment for other innovation. Without Firecracker, we would not have been able to build Fargate. Fargate allows you to run serverless containers, no longer having to think about infrastructure management. So, and also what came with that, and something I want to repeat from what I said last year, you have to build evolvable architectures because your architectures will change over time. And you need to make sure you can evolve them without impacting your customers. And that's sort of what we saw here with Lambda as well. We're very successful initially in getting feedback from our customers, how our customers were using it when we were running on the T2s, and then build an environment underneath there that really matches our costs with the pricing model that we gave our customers. Now, actually, let me take a step back. This is a fun story that one of the distinguished engineers of S3 at some moment told me about sort of the evolution of S3 over time. Yeah? S3 started off as a single-engine Cessna. Yeah, and then it was upgraded to a small jet. And then to a group of jets. And then eventually to a whole fleet of 380s that are refueling in midair and actually continuously have our customers moving from one plane to another plane without them ever noticing it. And that's the power of an evolvable architecture. But what I want you to walk with, this is a fun story, but what I really want you to walk away with is that when you are creating technical and economic debt, because you're not taking costs into account, you have to pay it off. My next observation is that architecting is always a series of trade-offs. And it's a series of trade-offs between non-functional requirements and the functional requirements that you have as a designer. Yeah, and so you can look at that sort of cost versus resilience versus security, all of this. Yeah? And so I can tell you stories about this at Amazon, but I'd rather have someone else with similar experiences tell you this story as well. And so my next guest has a great story to tell how they aligned their business and technical priorities to achieve remarkable growth. Please welcome on stage Kat Swettel, the Senior Director of Engineering at Nubank.
Thank you, Werner. I'm so honored to be here with you all today. With 90 million customers, Nubank is the 4th largest financial institution in Brazil and the 5th largest in Latin America. But only 10 years ago, we were just a few people in a little house in Sao Paulo. Back then, the majority of Brazilian banking institutions were managing mainframes and legacy systems. But with cloud technology, Nubank was able to disrupt the market, making banking more accessible for customers who never had access before. Nubank's journey all started in this casinha, the little house that I just told you about, where Nubankers worked on products that were built to be so efficient that we could charge much more reasonable fees. How did Nubank achieve such rapid growth in only 10 years? We were born on AWS, utilizing the new region that had just opened in Sao Paulo about a year and a half before our founding. And AWS is still Nubank's preferred cloud provider. Our first product was a credit card with no annual fee and an unparalleled customer experience. But that disruption was only the beginning. Soon we had a bank account, insurance, investments, loans, an in-app marketplace. The list just keeps growing. In under 10 years, our technical environment consisted of over 40 different AWS services underlying over 1,000 Clojure microservices. We were focused on growth and we were succeeding. Then, in 2020, the Brazilian central bank approached financial institutions with a radical new idea for how to transfer money. Before 2020, transfers between accounts in different Brazilian banks were slow and expensive. They took up to a full business day to complete and cost up to $5 US. Then, to incentivize financial inclusion, Brazil's central bank proposed a new protocol called PIX. For those of us in the US, PIX might be a strange concept. It's truly instant, real-time liquidation, zero cost to customers, available 24/7, 365, and all backed by the Brazilian central bank. meaning when someone transfers you money, it's instantly available in your account, your regular account, so that you can make a purchase or pay a bill. So we spent 5 months developing Nubank's PIX flows to meet the 10-second latency requirement dictated to us by the central bank. When it hit the market, PIX was a huge success, far outpacing the usage that Nubank had anticipated. In about a year, PIX transactions per month had exceeded the combined total of credit and debit transactions. The scale was massive, and it significantly increased load on our mobile app and our customer-facing flows. Our whole technical environment was under an unprecedented level of stress. At this point, we were in a bind. We were facing instability in multiple flows, driven by that increased PIX traffic. And we were also facing increased cost scrutiny as we transitioned as a company out of startup hypergrowth mode. How would we deal with the trade-off between cost and stability? For us, the answer was to choose both. We suspected that a lot of our exploding costs was just due to the misguided ways we were trying to achieve stability. In many cases, we were just throwing more machines, more memory, whatever, at the problem instead of actually solving the problem. Our hypothesis was that if we stabilized our systems, costs would also stabilize. With AWS, Nubank's PIX team spearheaded a multi-team effort to test that hypothesis. Of course, we initially addressed urgent architectural challenges, but we also made 3 less obvious but very impactful changes. For the first change, we noticed that some of Nubank's microservices were experiencing instability as a result of long garbage collector pauses. So in our quest for stable efficiency, we started to experiment with the Z garbage collector for those microservices that were experiencing the long stop the world GC pauses. Now, ZGC costs us more in RAM than the G1 garbage collector, and it really made no difference during steady state operations. But it dramatically decreased the maximum GC pause length, which saved time and money for some of our most critical services. After garbage collection was addressed, we started to look towards our database's caching strategy. Our canonical database, Datomic, is an append-only database that's backed by Amazon DynamoDB. Datomic makes use of an in-memory cache as well as Amazon Elasticache as an external cache. As the amount of data grew for some of our most critical services, data locality became a challenge, and more transactions had to hit that external cache. At first, we tried to just add more memory to beef up the local cache, but that proved pretty inefficient. So instead, we decided to start experimenting with a new caching strategy using NVMe disks, where we could cache a lot of data and query with pretty low latency. As just one example of the great results, for one of our critical microservices, for every $1 that we invested in NVMEs, we avoided spending $3,500 across those flows. So the stable option ended up being a net cost savings. Our culture also changed, and that was a big part of Nubank's success. In order to make important decisions and good trade-offs in context, leaders at Nubank need to have basic technical understanding of their products and our infrastructure. And that movement kind of started with the PIX leadership team, but the change quickly became a standard across the company. And today, business units at Nubank are expected to have an AWS cost champion to help leadership make informed decisions that balance competing concerns. In the case of PIX, our hypothesis had been proven true. Stable systems were efficient systems. Cost stabilized and became more predictable. Meanwhile, the time we spent in high-severity incidents decreased by an order of magnitude, and the P99 on our latency SLA decreased by 92%. In fact, with a remarkable 35% efficiency ratio, we stand as one of the most efficient companies in our sector. And that transformative impact has saved our 90 million customers $8 billion in fees in 2022. Nubank's growth is fueled by our low-cost operating platform and our efficiency, which allows us to charge less and invest more in our customers. Now, for every 2 adults in Brazil, 1 is a Nubank customer. And we hope to continue closing the gap and make banking accessible to all. Thank you.
One thing that really struck me was those words. The business needs to understand AWS costs. And I think someone wrote on Twitter, every engineering decision is a buying decision. Keep that in mind. And also like actually the way that they put their metrics available for everyone to watch. I know that when you start making your metrics visible, it can change behavior. You have to really figure out, and you think about sort of measurements and observability and things like that. And just like Nubank, I want you to work with your business to align your priorities. And the only way to do that is to really understand them. Now, next to those 3 laws that are considered to be in the design phase, you will continuously need to sort of understand where your costs over time are actually going. Unobserved systems lead to unknown costs. And I have a really great story here. My hometown of Amsterdam. Beautiful houses, old houses out of the 1600s and things like that. In the 70s, when I grew up, there was this oil crisis. I don't know if you remember that. We had carless Sundays. And of course, at that moment, everybody started to understand and started to become concerned about the cost of energy. And there's this great investigation at that time, because it turned out that there were houses that were almost identical, but some of those houses was used 1/3 less energy. Why was that? It was mind-blowing, because these houses were the same. By the way, there's no double glazing and things like that in those days yet. So these houses are just radiating heat the whole time. But some of them are radiating less heat. So what was the difference between those houses? The houses that used more energy had their meter in the basement. It was basically hidden. The houses that used less energy had their meter in the hallway. The fact that every time when you entered your house, you could see how much energy you had been using, completely changed behavior. And as such, you need to make sure, first of all, that you understand what you're measuring, of course, and how that measurement can change behavior. Now, if you're in retail, for like Amazon.com, there's a number of costs that you actually always have to keep in mind. On one hand, remember, Amazon is a massively microsystems-driven environment, where each of the costs to a particular service, each of the requests to a service will have a certain cost. Now, of course, it's often hard to measure that, but you need to. You also need to, if you have actually one top-level request that goes out to all these microservices, you need to be able to get the aggregate of that. And then you need to figure out what is actually my conversion for each of those requests. And actually, so there's literally dozens of features on an Amazon homepage, and each of them may go out actually to hundreds of backend services. So you need to actually sort of decompose this. And all of these features that you can decompose into come at a certain cost. What's the total cost of this experience? And you can actually measure those individual costs. You actually have to measure at microservice level. You have to isolate these ones still. For example, the service that can give you an estimation of delivery speed. How much does that cost me to do this? And of course, the easiest way would actually be to just take it over a certain period of time, take the number of requests, divide them. That's a little bit simple, but it's a good approximation for you to think about. Yeah, if your cost is a normal distribution, then that probably will work. More importantly, over time, your costs should be going down. If you don't make any changes to this, and not even maybe some economies of scale, but also you should be able to re-architect, to do profiling, to start looking at sort of moving maybe from one architecture to gravitons, all these different things that you can do to actually drive your costs down. So over time, the cost per request to this microservice should be getting down. And then on top of that, you have to figure out what your transit costs are. Yeah? What is the cost of serving this application or this web page for you? What's the total cost? Yeah? Can you figure that one out? Now, I'm going to show you now a slide, and just like when I saw it for the first time, you're going to scratch your head. This is the number of microservices in the back end of Amazon.com. Yeah, my request to the homepage originates over there, goes out to all the other microservices to construct this page for you. And you can dive deep into them, in each of them. You can figure out what the cost is of the individual ones, the ones that are actually, again, making calls to other microservices. But you need to understand the complete picture, the complete cost picture that this one page, this homepage, actually costs. And you can, because remember, in AWS, each of the resources that you've been using comes with a dollar tag associated with it. So you know exactly the cost of every single one of these services, and we know the cost of the whole system. And then, of course, you need to figure out, you know, what is actually the contribution of each and one of these features to my conversion rate. Yeah, you need to also understand the value of new features. If you start actually spending more money on actually creating this page for you, you should see your revenue coming up. You shouldn't see it actually flattening out, because that means you're making investments that have no return on investment. And there are indeed diminishing returns at some moment. Now, one of the things that we are very strong at and probably everyone else that actually has a web application, is that you understand there's this common knowledge that improving latency of your web pages will improve conversion. So if you build an evolvable architecture, you probably also make it easy to actually experiment. So imagine that your 99% percentile for your web page latency is 1.7 seconds. If you can engineer that to bring to 1.6, you know how much that's going to cost you, how many more resources, and you can see what the impact is on conversion. And at some moment, bringing in the latency does no longer have a return on that. Measure that. Think about how to measure that and make it up front. Make sure that everybody understands that. Yeah, you have to know your cost. And I think it's often, it's complex. As you see, the application that I just saw you, the backend for Amazon.com, is a pretty complex environment. But we have made this really our own, because we need to understand it. Retail margins are razor thin. We need to have total control over our cost at any time. Now, I also know that quite a few of you are literally running hundreds of applications. And it's sometimes really difficult to really understand sort of what are the metrics that belong to this particular one application. And you've been asking this for quite a while, and I'm happy to announce today, myApplications. It basically gives you a new experience in the AWS control. It gives you visibility to cost, health, security, performance, per application. Yeah? What you can do there is basically, we have a new application tag, you assign that to the resources that make up your application, and then you get a single view of this observability into many of the standard functional requirements, non-functional requirements, and cost. And with cost, also a proxy of sustainability. Now, sometimes it's hard to instrument your applications. Especially these days, if you start off with Kubernetes, for example, with EKS, and you're building this distributed application with many containers and container types and things like that, in instrumenting them in a way so that you get a good holistic view of them is not always easy. And you need to do it in a consistent way. So, and I know that's a lot of work. So I'm happy that today we make available for you what's called CloudWatch application signals, such that it will automatically instrument the EKS applications that you're building. Yeah, so that you can have one single dashboard immediately looking at all the metrics that are relevant for your EKS application. With all of that, I want you to walk away with this thing. Yeah? Define your meter. Because if you can continue to look at this meter, it will change the behavior. And make sure that your meter includes cost and sustainability. Now, another observation I had that, if you build cost-aware architectures, you need to implement cost controls. Now, you can't just rely on good intentions. You need to put mechanisms in place. And as such, you need to build and have it at your fingertips, and you have it in the cloud, tunable architectures. And remember, in AWS, the knobs always go to 11. Oh, come on, you must have watched Spinal Tap. I don't care if you clap on lounges or not, whatever. But if I make a joke, I would really like it if you would laugh. Yeah? Now, okay, go back. What was I doing? So software changes, software choices like database types, API languages, and well-designed systems of NFRs, they allow this tuning. Yeah, and if you look, bringing it back to Amazon.com again, you imagine that on this homepage there are all these different components. Yeah, and you need to have controls to manipulate those components. Imagine what you're seeing is either cost or performance or one of the other metrics that you're following is going out of bounds. You need to be able to switch some of those components off. And that's really important. But you need to build the switch, but the switch should be in the hand of the business. It should not only be something where you as a technologist makes a decision, it's a decision that you make in concert with the business. Yeah, because after all, that's who we are serving. That's who we are working with. Yeah? But you need to have these switches and dials available, so that you can make these decisions. Crucial in all of that is to be able to do decomposition of your application that you have. Start to figure out which are the things in your application that are really, truly important, medium important, maybe not that much. Yeah? If you think about Amazon retail again, what is important? What always needs to work to have the application work? Search, browse, shopping cart, checkout. Without that, we're dead in the water. The system, the application, doesn't work. And then there's a tier 2, we call that tier 1. Tier 2 are maybe features such as recommendations, personalization, similarities. Things that really are important for the customer to actually discover the products that they're looking for, but they're not part of the true core of the application. One of the things that actually moved from tier 2 into tier 1 is reviews. It turns out if reviews are offline, customers are not buying because they trust the opinion of their peers. And so you have to make decisions then together with the business to make these trade-offs. How much am I willing to spend on fault tolerance of tier 1? Probably as much as you can. Because that always needs to be on, because without that, you don't have a business. Replicate over 3 AZs at minimum. Maybe for tier 2, you're willing to actually dial it down a little bit. Maybe for tier 2, replicating over 2 AZs is sufficient. And for tier 3, bestseller list, who cares? If they're offline for 5 minutes, it doesn't really have impact on the customer experience. So you may have a different type of resilience there in mind. But make sure that all of these pieces are controllable. And whether you switch them off already throttle them, or already maybe turn off prefetching. You know what we do, we actually search for something. We look at what is the most likely products that you're looking for and then start prefetching them to make sure you're faster. Maybe you turn that off. Maybe fewer details. But all of these knobs, all of these controls are for the business. You have to give control to your customers. So with all of that, what's my advice there is, establish your tiers. Start thinking about which are the pieces of my system that absolutely need to be up and running with predictable performance all the time. Now, if I think about sort of about optimization, there is another, what I consider, lost art. Given that we have been able to focus on really fast innovation, and we've been moving really fast, and something that we did when we actually were living within the constraints was really tinkering at a smaller level. But that tinkering at a smaller level is becoming more and more important because it turns out quite a few of your costs are actually going there. You need to start thinking about what is sort of the digital waste that is laying around in my system. Yeah? What are the things that I can just stop? Maybe the business doesn't like it anymore. PBS said they had one particular series that maybe someone watched twice a month or something like that. And they still had it running. They managed to turn it off. When you go home at night, do you turn off your development environment? You should. There's no reason to keep that running at night. Yeah? Or maybe right-sizing. Move to a smaller instance, or maybe to a bigger instance. Or, more importantly, move over to Graviton, so you really can drive your costs down. Or maybe, start thinking about how to reduce the kind of capabilities that you are presenting to your customers. Is it really necessary to stream in 8K? Is it really necessary to send this 5 megabyte image over that then the browser actually puts it down to 600 by 100 pixels? Is that really necessary? Start becoming smart with that. Reduce it to actually the amount of resources that you really need for your application. Now, when I think about this lost art, I think about profiling. I don't know how many of you grew up with this, but this was in my toolbox when I was in school. You really needed to be able to dive deep, to be able to understand exactly at function call level where your time was going. A Code Guru profiler actually gives you this as well, next to the language profilers that you just saw. A profiler will in general generate something like this flame graph. This is actually of a real Amazon service. I'm not going to tell you which one, but you can actually dive deep into this and figure out where your cost is going. You see, 8% is going into garbage collection. That's your choice of programming language over there. It impacts that. But there's a large part left over here. And that's turned out to be network communication. And that's kind of out of balance. That's not what we would expect in that particular case. And then diving into the code, you suddenly start to understand what happened there. When they were designing this, they had a common case in mind. And then for anything, maybe 99.9% were the common case, and the 0.1%, they would throw an exception for. Turned out, they didn't really expect that it was the inverse of that. 99% of the packages came in, hit the exception. And so by simply changing this exception handling into an if-then-else statement, basically completely removed all the processing that was necessary there, the exception processing. And then, this is the if-then-else. And what happened then is that we actually went from 42% down to 27%. So this is actually a process that you continuously need to do. Even if you don't find, let's say, these big disparities, you still have to understand exactly where your cycles are going. And this is a continuous process. It doesn't stop after day one. You need to completely understand it. Especially, wouldn't be the first time that I've heard from customers say, why is the backend service for our iOS app so much more expensive than the one for our Android app? Well, maybe you should start looking at how they're implemented. And the power of profiling allows you to be curious and dive deep. Now, the last one, my observation, may be a little bit more controversial. Yeah? And so please hold on to your egos at this particular moment. Yeah? The most dangerous phrase in the English language is, "We have always done it this way." Yeah? Rear Admiral Grace Hopper, the grandmother of all those developers here, was a very wise woman. And it wouldn't be the first time that I come at a customer who says, "Yeah, but we're a Java shop. Oh, we're really great at Rails. Yeah, we've always done it like that. And we've done this before in my previous company. We're going to do exactly the same." You have to keep in mind that development is quite often expensive. But the cost to build dwarfs to the cost of operating your applications. That's something you have to keep in mind. And the way that you build your applications, the platforms you use, the programming languages you're in, should be continuously under scrutiny whether you are picking the right one. Now, I mentioned earlier that I thought that cost was a good approximation for sustainability. Maybe the other way around as well. There isn't that terribly much research into how much certain programming languages will cost you. However, there is brilliant research by Rui Pereira at UESC in Portugal about the energy usage of programming languages. And so he first launched this paper in 2017, and it shocked the development world. He released this paper with much deeper insight, much deeper showing different types of applications that were being built. Turns out, Ruby and Python are more than 50 times as expensive as that C++ and Rust are. Now, I know the reasons why you wouldn't want to use C++ with all the security risks that there are, but there is no reason why you should not be programming in Rust if you are considering cost and sustainability to be high priorities. We implemented Firecracker in Rust. Large parts of S3 are re-implemented in Rust. And not only because the energy usage is lower, which we aim for, but also because the security, the strong typing, the memory safety that you get in a fast, efficient language like Rust is very important. Now, with all of this, I don't want you to immediately start sort of throwing away everything that you know and starting over. But we as technologists live in a world that is moving so fast that we always need to continue to learn. We always need to disconfirm our own beliefs. Yeah? Put your ego aside as being the master Java programmer, but start thinking about the cost, actually, and the complexity of how to deal with garbage collection. Start thinking about that maybe this massive platform underneath there, maybe that's costing you a lot, even though it allows you to do very fast prototyping. So disconfirm your beliefs. Now, so these have been sort of my observations around cost and sustainability that I've learned over time at Amazon.com. Yeah. Cost awareness is a lost art. We have to regain this art. Mostly also because sustainability is a freight train that is coming your way that you cannot escape and should not escape. And cost is a pretty good approximation for the amount of resources that you've used. The constraints from the past, I don't want to go back to them. But we may actually be willing to have self-imposed constraints. Put some constraints around the systems that you're building in terms of cost and sustainability. That's why I believe that constraints, even self-imposed, can breed creativity. Now, with that, I think the frugal architect is live. At this moment, not that there is that terribly much information, but I would love to work with you actually to incorporate your cost awareness learnings in it over time as well. So the site is thefrugalarchitect.com. Sorry, give me one moment.
Not what you were expecting.
Probably more private islands and sailboats.
Ah, not that, Oracle. I'm sometimes right about the future. Actually, that's why you're here. I need your insight.
Everything fails all the time, even the simplest of hardware.
You see, I have been asked to use my gift to make some tech predictions for La Predictor magazine. And I've heard that you are something of a tech soothsayer.
So, what are your predictions up to now?
Envisage, if you will, a world where artificial intelligence is represented by an omnipresent, benevolent attendant. It will revolutionize industries like healthcare, freeing medical maestros from administrative burden.
That's not really the future. Healthcare is already deeply ingrained in very advanced analytics and machine learning.
Okay, how about this? Dare to dream of a future where developers are no longer solitary mavens coding within the confines of individual experience. No, the builders of the future will dance side by side with AI in a celestial ballet of organic digital pair programming.
I'm not feeling that either. Code Whisperer is already here. That future is now. No dance necessary.
All right. You are gonna love this one. La pièce de résistance. Hoverboards.
No. Let me stop you there right away. That's not gonna McFly.
Making tech predictions is tough.
Well, the future is not science fiction. To be able to make good predictions, you have to think about the present. Because the future is now.
Before you go, here, have a cookie.
No, I only accept essential cookies.
So I'm not an oracle. But observing the present actually helps kind of predict the future, and that is especially at AWS. The kind of things that we're doing at AWS often defines the technical future. And that is actually really important. But I also think that historical context is important. Look at the bigger picture, look a bit back. And I know that we've all seen amazing innovations being presented to you this week in the area of Gen AI and LLMs and how we're going to change development and how businesses are going to change. But where did this actually come from? What is the history of this? It goes back to two of my favorite early Greek philosophers, Plato and Aristotle. Both of them were thinking about whether machines could actually do the tasks of humans. And they were thinking about sort of what is it actually that controls humans? Aristotle thought it was the heart, the soul, that actually drove humans. But Plato actually thought it was symbolics in your head. And actually Plato went as far, if you read the Republic, that he created a city-state in that book where actually machines, robots, were doing the chores. Now, that's about, 25 centuries ago. Not much happened for about 25 centuries in that sense, until the first computers arrived. And computers could do much more than just calculations. They were capable of more complex tasks, and as such, everybody started thinking that, oh, maybe if the human is indeed driven by sort of this symbolic complexity in their head, maybe we can use computers for that as well. And of course, one of our more important philosophers of the last century, Alan Turing, spent a lot of time on that. He really started to think about, can machines, computers, think? Yeah? And his famous paper in 1950, Computing Machines and Intelligence, is really sort of the groundbreaking work that we still live by. We still talk about the Turing test. Now, unfortunately, Turing tragically died before he could join this 1956 workshop at Dartmouth. In this workshop, the term artificial intelligence was coined for the first time. But still, most of the researchers available there were from the symbolic AI field. They're really thinking about sort of, can we implement reasoning? Can we implement this symbolic reasoning? Can we use mathematics for those kind of things? Didn't really go anywhere, not immediately, at least. These automated reasoning and things like that have become tools that are incredibly important, but not necessarily in the field of AI as we know it now. One of the things that we did start to build in those days was called expert systems. I built a few of those using Prolog. And I still don't like the curtains behind it. So expert systems actually sort of incorporated knowledge in rules, and then you could execute queries against it and sort of get answers back. But they were very laborious, and they weren't, to be honest, they weren't that terribly smart. The big breakthrough came when we saw this shift happening from symbolic AI to embodied AI. And what did that mean? It's basically that groups of researchers started to think, if we start to have these basic building blocks that humans have to perform tasks, maybe out of that we can build artificial intelligence. It is mostly driven by the idea of that you have robots. What are the kind of capabilities that robots need? What are the kind of sensors that we have that we need to give robots? Speech recognition, image recognition, and even maybe sensors that we as humans don't even have, like LiDAR. Now, can we build that ourselves? And that thinking actually has driven us for the past 10, 15 years. And we saw new algorithms arriving, deep learning became important, reinforcement learning, all those different types. And what we saw was software improved, algorithms improved, hardware started to improve, software improved again. And we saw a really quick acceleration of all these different algorithms happening such that we could do better learning, better build these big models that could actually help us do tasks. Now, of course, the next step, the most recent one that has created this sort of earthquake in the world of AI has been transformers. The ability to use transformers to build foundational models and to build these large language models are actually a revolution in all of this. Yeah? But I'm not going to talk about that, really. I really want to go back one step and talk about what I would call good, old-fashioned AI. Yeah? The cool thing is that now we have good, old-fashioned AI, and there is new AI. The new AI doesn't invalidate the old AI that we were having. Yeah? And so if I look at so many of my customers who have built amazing systems using good old-fashioned AI, that I think you should keep in mind that not everything needs to be done with these massive large language models. Yep. And I'll pick a particular area. I've, over the years, become extremely interested in those businesses that actually are combining two things. They are trying to solve really hard human problems and use technology to do that. Now, I could give you lots of examples of companies that have done amazing things with AI for now, but I will pick a few out of my out of my box of these companies that have built things for AI for good. And so one of them is one of my most favorite organizations to work with. It's the International Rice Research Institute. They sit just outside of Manila. And their mission is to abolish poverty and hunger among rice-dependent communities. You have to remember that the prediction is by 2025, the population has grown by another 25%. How are we going to feed them? How are we going to make sure that that happens? So they're an amazing organization. They have a massive seed bank, big freezer actually with 200,000 strands of rice in them. They can regrow any type of rice. They can also make improvements to rice. For example, golden rice is a good example that has much higher degrees of vitamin A in, which is very important for certain communities. And so, but they had a big backlog because all these seeds are being sent to them and humans need to sort of sort them and try to figure out which of those seeds are actually useful and which they should be storing. And they got a backlog and everything in the backlog starts to deteriorate. So they basically make use of machine learning and vision management to actually automate this process. Not that they are actually, the machine is actually now making the decisions which seeds should go into the bank. Still humans do that. But the automation before that, the efficiency before that, using vision, allows them to actually remove the complete backlog. They improve their backlog, the sorting productivity by something like 30 to 40%. Surgenics, another very interesting company that I recently met in Ireland, apparently, and this was not a problem I was aware of, that most infants that may be born with brainal injuries that are not immediately visible, often those injuries aren't visible until months or even years later. They have a very simple test, a small cap that basically takes an EEG of the baby and immediately can determine whether a baby actually may have that particular injury. And as such, you can immediately start treating them, which actually improves the quality of life for these babies for a very long time. So what they did, they actually have all the scans, they put it in a tree, ran it through SageMaker, created this model, which is very unique because baby EEGs are radically different from that of adults. So their goal is to make this brain testing for infants as commonplace as the hearing test that each baby is getting now as well. Another company, Precision AI, we've all seen drones. Drones are basically a box full of AI capabilities. After all, we're not steering them. We're giving them a task and they need to go away. They need to go somewhere. They need to follow a particular pattern. They need to avoid birds. They need to avoid washing lines. They need to do all these things by themselves autonomously. So they're a big AI box to start off with. Precision AI has as a task to avoid that complete plots of land are sprayed with chemicals to remove weeds. They fly over this patch of land, create a map of it, and are then able to attack individual weed plants, significantly reducing the runoff of these dangerous chemicals in the creeks and rivers surrounding the plot of land. Digital Earth, Africa, another one of my favorite companies to work with. They make use of, there's an open data set of satellite imagery of Africa. And this data is being used by governments all over the place. In Zanzibar, for example, they're monitoring coastal erosion. In Ghana, they identify the impact of illegal mining. There's these illegal roads being built that go to these mines. And in South Africa, Kenya, they understand the impact of forest fires. All of this is driven by this open data set of Digital Earth Africa. And many of these organizations are using this to improve the life of Africans across the continent. Now all of this, and I think Swami hammered down on this point as well, without good data, there is no good AI. And so in the past, indeed, we had all the structured data. If you think about patient records, that was a structured record. These days, patient records have all sorts of unstructured information scribbled all over them. And so here, suddenly, you have a mountain of unstructured data where you think this may be a haystack that has a needle in it. So how do you find a needle in a haystack? You use a magnet. And the magnet is machine learning. Yeah? Basically, you use machine learning to create meaning out of this mayhem. And this AI for now actually gives you practical solutions for real problems. And it's incredible to see what customers can build with these services and the tools that we provide. And they've leveraged AWS to solve some really hard problems. A prime example of that is an organization called Thorn. Now, our next speaker is going to talk about child sexual abuse. And I recognize this can be this is a difficult topic. Yeah? I encourage you to do what you need to do. Take care of your well-being. But I'd like to welcome Dr. Rebecca Portnoff on stage to discuss how Thorn utilizes AI to protect children.
I'm going to tell you a story, a true story. A child is being sexually abused. We'll call her Maria. Maria's abuser is taking pictures while he abuses her, and then sharing these images and videos onto a content hosting platform, hiding in plain sight among hundreds of millions of other images and videos. But this particular platform doesn't accept this. This platform uses Thorn's Safer product. It uses Safer's Child Sexual Abuse Material, or CSAM classifier, to find images and videos that could show a child in an active abuse situation. And one day, the classifier alerts them they've got a hit. So they go to work, and here's what they find. A user has shared over 2,000 new abuse files. It's clear a child is being abused. So they flag the case to law enforcement, who launch an investigation. And the child in that content, she is found. Maria is found. An arrest is made, a recovery is complete, and for Maria, a brighter future emerges. This isn't just a story. This is reality. This is the gravity of our work. We as technologists, we have the power to end a child's real-life nightmare. Our challenge, how do we find them and stop the cycle of trauma? The answer to these questions are buried in haystacks of data. So then, what's that right magnet to find that needle in a haystack? The answer is complex, and an essential part of it lies with machine learning. According to the National Center for Missing and Exploited Children, in 2022, they received over 88 million files of suspected child sexual abuse reported to them by online platforms. Now, these aren't just files. These are kids who desperately need help. Think about it. With 88 million files and even just 1 second of review per file, that's going to be almost 3 years of nonstop review. I don't want any kid to have to wait that long to get help. We are a nonprofit that builds technology to combat child sexual abuse at scale. AWS is our preferred cloud provider in this work. We leverage AWS services to power our machine learning tools. I have dedicated my career to defending children from sexual abuse. So I can tell you with confidence here today, machine learning AI, it does make a difference. We build safer. So we built Safer, our all-in-one tool to detect, review, and report child sexual abuse material. Safer uses hashing and matching to find known abuse material content that's already been verified by an analyst, and the classifier to find new abuse material. My team at Thorn, we built the classifier to act as that powerful magnet to find new child sexual abuse material at scale. Now, when we first started building the classifier back in 2019, there was already active research on the use of convolutional neural networks for detecting child sexual abuse. But we needed a classifier that went beyond research, something that worked at a production scale. When we build a classifier, we follow the CRISP-DM process. As you can see, it's really all about the data. But within this broader framework, we had to overcome a key hurdle. This data is illegal. Child sexual abuse material is illegal. You can't store it in the same places or the same way as other content. So the solution was to collaborate. We invested in hardware installed on-site at organizations with the legal right to house this data, training the classifier on-prem, and then using Amazon's ECR to distribute that trained model to end users. So we've got this critical training infrastructure in place, and now we can build, starting with data prep. We use techniques like perceptual hashing to deduplicate the data set, ensuring that there's no overlap between the training, testing, and validation sets. We use Amazon S3 to store our non-abuse material. And this data is just as important as the abuse material for training our classifier. Now, model training via remote access to an on-prem solution, it's got its challenges. It can be slow and opaque. So we use Amazon EC2 and EKS to do R&D with benign data first, debugging and fixing any issues we may find in our training pipeline before training on-prem. In the machine learning AI lifecycle of develop, deploy, maintain, that maintain part is key because models get stale and models have bias. So what this means is monitoring performance and regular retrains. What's our performance holistically? And then drilling down. Is our model better at classifying abuse material of lighter skin or darker skinned children? What kind of trends are we hearing from users about false positives and false negatives? Because to fix a problem, we have to first know what that problem is. Then we balance our data sets, adjust the model weights, refresh our training data set with new images, and retrain. Now, AWS powers our user feedback. We have an API in our AWS-hosted Safer services where users can submit false positives to incorporate back into our training. These false positives are often the most valuable negative examples that we have because they allow us to do targeted retrains and improve performance on data in the wild. Now, none of this hard work that I talked about matters at all if you can't get the classifier into the hands of the users. So effective model deployment is key, working collaboratively with engineering and product to find the right solution for the user's needs. And when I say effective deployment, I'm specifically thinking privacy forward and human in the loop. I am proud and thankful for how Thorn's engineers deploy the classifier in a way that the customer has full control over when and how the content is reviewed and reported. Because the classifier, it acts as that powerful magnet, but it should be a human making the final call on what gets reported. Now, we are all here today because we want to build something that has impact. So what's that impact look like for Thorn and our partners? It looks like the outcome of the true story I told you earlier. A child gets her life back. It looks like over 2.8 million potential files of child sexual abuse found via Safer. It looks like constant innovation. This month, we launched Safer Essential, an API-based solution for quick detection of known child sexual abuse material. This is a future where every child is free to simply be a kid. And everything we build at Thorn, it's to get to that future. But that technology by itself is never going to be enough. Having impact requires all of us to work together. Content hosting platforms, law enforcement, government, survivor services, and the community, including you in this room. And I want to do that together with you. I want everyone here to join Thorn in our mission. I want you to show up at the Nonprofit Impact Lounge today and ask my amazing colleagues at Thorn how you can use our technology. And I want you to go to thorn.org and learn. Learn about what these kids are going through and what technology can do to help them. And then I want you to pick up your laptop and build what these kids need. There are still countless victims who are suffering, but we have the power to help them if we work together. Thank you.
This is the power of technology. And the power that we have. Yeah? Make sure that the call to action that Rebecca just gave us doesn't go wasted. We have that power to absolutely make a difference as technologists. Yeah? With the right technology and the right access to data, we can have a really positive impact on the world. And technology can be a force for good. Yeah? That's actually a lesson I learned way before I ended up in computer science. Yeah? That's me on the right there. Yes, I had hair at some moment. Before I started computer science, studying computer science, I worked in radiology. Both radio diagnostics as well as radiotherapy at the Dutch National Cancer Research Hospital. And a lot of technology was already part of that. Not just the fundamental X-ray technology, but CAT scans, MRI scans, nuclear imagery, all was sort of starting out. By the way, that is 40 years ago. This is not, by the way, a fancy Gen AI picture. Yeah? The person sitting in front of me is Frank de Leeuw, to who I owe my computer science career. Frank is a radiologist, and Frank was probably the most passionate medical doctor I've ever met in my life. Frank wouldn't go home at night until he had all his work done. That meant at 10, 11 o'clock at night, he would still be sitting in front looking at his imagery, because he knew that if he wouldn't finish it that day, the next day would start with a backlog and he would have that amount of work yet again. And so he worked really long hours. And I really admired him. But he kept hammering on me that I should leave the profession. Because he felt that, given that I had a sort of an affinity for technology, he felt that my skills were much better used in actually building technology that could help people. And I really took that to heart. I basically went back to school again. And it's his fault. It's also his fault that I'm here now. So I started thinking, and I have a real affinity still for all the work that we were doing in those days. And it got me thinking, can I build something useful with ML? Can I do that myself? After all, I've been telling all of you for years now how easy it is to integrate ML into your applications. However, I needed to make sure and really wanted to do this myself. So what do? Actually, I tried to catch up on 40 years of radiology work, innovations, talk to doctors, go to hospitals, understand what the current problem space is, and try and find one particular problem, a small problem, that maybe I could try to see how much work it would be to build a solution for that. And I took some courses in ML University, spoke to AWS ML experts and things like that, just to get me up to speed, not just about the principles, but about the practicality of it. And one of these, in this hospital in Dublin, where I talked to one of the stroke specialists, he hammered on me saying that every second when a person has a stroke counts. A stroke patient loses 1.9 million neurons a minute if they're not being treated. So quick treatment is crucial. Okay, that sounds like a reasonable, simple enough problem that I can attack looking at brain hemorrhage in X-rays. And if it would be like this, in case you can't read it, the big white spots there are basically blood hemorrhages in the brain. If they would be this big, that would be easy. But often they're not. They're micro lesions, or really sort of continuous micro strokes and things like that you can still detect using CAT and MRI scans, but it's much harder. And so I was starting off thinking like, can I build an ML pipeline that sort of can sort of decide whether on an image there is actually a brain hemorrhage. And then if you would actually find a positive, you would actually sort of prioritize that in a radiologist work list so that it could be immediately evaluated. So as all with that, if you don't have good data, you don't have good AI. So that is immediately step number one of my stumbling block. How would I get access to data and imagery that I actually could train my model on? Well, actually, turned out that was not that hard. Kaggle has a data set with 700,000 pre-labeled CT brain scans. Yeah? That allowed me to actually immediately get off to a start. So download that set, put it in S3, and as always, with, when you do this, you sort of split the data set up into the set where you're going to train it with, how you're going to validate it, and how you later on are going to test whether the model actually works. Yeah? 17, 15, 15 is a common practice there. Next thing to do, fire up SageMaker, push this button, and now I have to write some code. And so pretty common in that is you're actually using Python. And if you just realized, I'm not necessarily that proficient in Python. But the Python SDK actually has a whole bunch of built-in algorithms and pre-trained models from popular open source model hubs that you can immediately use. So I selected an architecture that I've researched, and I can fine-tune it with my data set. So the only thing to do now is actually to add the code, to launch the training job, push a button, and it gets immediately scanned through, and this model gets created. Wow, that's easy. However, under that button push that I did, there is a lot of work happening. Yeah? And I don't know if you know much about sort of deep learning and how these models are being built with multiple layers and things like that. Basically, you push an image through, goes forward, goes that, and a loss score is being calculated. The loss score needs to be as low as possible. Yeah, the lower the loss score, the higher the accuracy of the model that you've built. Okay, if the number is high, you basically go back, you backtrack, and you adjust the weights and the biases in the model, and then you go forward again and to see what the outcome is, and you go backward again. And you do that for 700,000 images. Oh no, 70% of the 700,000 images. Yeah? And at the end of this pass always, you end up, you have forward pass, backward pass, forward pass again. Yeah? And all of this happens under the covers when I push that one particular button. Pretty amazing. And so then you get actually out of that, you get a model. And again, with one click of a button, I actually get an API endpoint for this model, where I can start putting my imagery through and get a prediction score, what the likelihood is that this CT scan brain image actually has a hemorrhage in it. And actually, it turns out it works pretty well. I was quite proud of myself when I built this. And of course, then, being the person that likes evolvable architectures, I start plugging all these different AWS components around it, reorganize the radiologist work list. And then something came to mind that when I visited that hospital in Dublin, where the neurologist actually said that he rather gets waken up at night at 3 a.m. for a false positive than not being waken up at all. Because every minute counts. So he doesn't want to wait until the radiologist gets to his reprioritized work list. He wants to get an SMS at night at the moment that my model detects that there is a brain hemorrhage. Yep. Evolvable architecture. Yep, added SMS, can actually send an SMS to the neurologist, and he can immediately on his phone take a look at the image, whether or not he should immediately jump in his car and drive to the hospital. It is that simple. It is not that hard to build these models. Anybody has been talking to you about AI and ML and building these models, how hard it is not that hard. Yeah? And actually, by the way, this is in no way a production system. This is my hacking on a Friday afternoon 5 weeks in a row. And of course you can start augmenting it because, as always, when you do one thing, you want to do all the other things. You could do, for example, use class activation maps, which sort of indicate what is it actually in this image that the model was actually looking at. And again, building a machine learning model is really sort of an interactive cycle. Now, as I said, this is in no way a production system. But, however, I'm very, very happy that a number of people on the AWS team actually did pick it up. And I'd like to thank Priya, Wale, and Ekta for actually taking my horrible code and turn it into something that might be a learning experience for you guys as well. So all of this is available for you on GitHub to experiment with and to see how easy it is to actually start building these ML models. And this is really what I want you to walk away with. If I can do it, you can do it. Yeah. Important in all of this, and we've talked about large language models, small models, whatever. Important in this particular case is that the model is small, fast, and inexpensive. Why is that? Because the hospital will want to run this for every brain scan that is happening. Yeah? And that is many, many of them a day. And they would really like to run the model locally, not require some massive compute power behind it. So for them, small, fast, and inexpensive is crucial to make this technology work for them. Yeah? After all, if you're using ML, you should still be a frugal architect. Now, talking to radiologists about sort of the future and what kind of the newer types of AI have there to offer to them. And if you think about that and talking to them, they would really like to have more of these what I call conversational interfaces. Because you have to keep in mind that a CAT on an MRI scan or nuclear imagery is not just one image. It's literally hundreds or thousands of slices for your body in digital format. We just happen to make imagery out of it because that's the census that we have. Yeah. They will really, and often, patients come to a hospital not with a clear symptom that really leads to one diagnosis. Now, often these are sort of unknown. And the radiologist's job is much more like an explorer, trying more than just being an image reader. And they really look forward to a world where there are AI-based radiologist assistants that could allow them to explore the data that they have at their fingertips, not just looking at images. And it also could include other clinical data. So suddenly, radiologists get a 360-degree view of sort of the state of the patient. Yeah? And it really helps driving diagnosis much faster than they could do before. They're really looking forward to the next generation of AI that helps them to build these conversational assistant interfaces. Those interfaces, though, will still make use of these small, fast, and inexpensive models on the side as agents to dive into specific problems that a patient may be experiencing. Again, I want to hammer this down. I think Swami did that yesterday as well. AI makes predictions. Professionals decide. They're assistants. They don't make the decisions for you. We, as humans, are the ones that make the decisions. Now think about us as builders. Think about all the news that we've heard in the past days. What's the impact of that on our profession, on our jobs? Yeah? And it always has been my passion to help builders be successful. And I hope that some of the tools that you've seen this week actually are going to change the way that you build your systems. And I think there's two ways that we see sort of generative AI impacting our world. Yeah? On one hand, how to incorporate generative AI into the applications that you're building. Yeah? And I actually, given that I'm a big fan of the CDK, the Cloud Development Kit, this is a project on GitHub that actually has these CDK constructs for generative AI. Meaning that if you're building an application with the CDK, you can build data ingestion pipelines, you can build question answering systems, document summarization, Lambda layers, all these kind of things straight out of the CDK. Check it out. The other way is, and I think that's probably going to have the biggest impact on all of us, is the collaboration between us and these coding assistants that are arriving now. Many of you have already been familiar with Code Whisperer. Yeah, and actually, I don't know if you saw this, but when I was developing the radiology application, I actually used Python, yeah, but Code Whisperer helped me actually implement that. Yeah, I didn't have to think about that. It actually helped me sort of look at these APIs that are unfamiliar, and the language isn't that particularly familiar for me. You might also have noticed that I wasn't using a notebook. Jupyter notebooks are the common way in which you sort of describe the machine learning project that you're working on. I rather work in VS Code than in a new development environment. So I'm happy, I don't know if you noticed that, there was sort of an Easter egg in that part, but you can now fire up a code editor from inside SageMaker Studio. Yeah, it's based on the open source version of VS Code and allows you to actually within SageMaker Studio work in the environment that is already familiar for you, which is VS Code. And you can launch this full-blown code editor with all the additional AI-powered tools like Code Whisperer directly in the IDE from SageMaker. But I think the biggest part, and I think I hinted at that before, we have a lifelong learning ahead of us. Technology has changed rapidly in the past, was it year? Imagine what's going to happen in the coming year, or in the coming 5 years. We need to be able to stay ahead of that. And for you, it's important to learn and be curious. Yeah? It will help you to actually accept these tools that allow you to explore new problem spaces and languages. It's becoming a creative tool, a sounding board for your ideas and approaches. Yeah, and on Adam's keynote on Tuesday, you heard about Amazon Q. And I think this is absolutely set to transform many aspects of software development. Yeah, you suddenly get an expert assistant in building on AWS sitting next to you. Yeah, it will reduce busy work and free up you to do more higher value work. And especially if you think about sort of the cloud space with all technologies in and around it, it is mind-blowing. This is too much for a single person to be an expert in. However, these AI assistants can be an expert in all of that and can help you work through that. Yeah, it can go from cloud computing solutions, machine learning algorithms, options are endless. And this is not a bad thing, it's just a very exciting time to be a developer. It really is too much for a single person to keep in their head, and that's where Q comes in. Yeah, I could take an example from earlier in the keynote. It could say, what AWS services do I need to start building machine learning models? And Q will give me a starting point. Or, it's not just a one-shot thing. It's not just a copy and paste kind of thing. It is a ask, adjust, iterate, back and forth, understanding all of these different things that you want to achieve. Yeah, and help you make a plan how to attack the problem space that you're looking for. There's more than just questions, yeah? Q actually is integrated in quite a few other pieces, yeah? For example, in Code Catalyst. It can help you start a project immediately inside Code Catalyst. It can generate an entire new feature for you, or a new approach. And I find it a really great way to actually start learning about technology, even though you may even kill the pull request that it created for you. It's just a great learning tool to understand the complete code base, to understand not just at a file level, but at an overall system level. And of course, Q sits in your IDE. So it can help you there. You can ask it to explain or create code for you. And through conversations, it can adjust and iterate. And in the fullness of time, we will see Q operate on each of the different pieces of our development pipeline. Yeah? And one example, for example, is the use of Q and Application Composer. I announced that last year, and I'm happy actually that Application Composer now is available within VS Code. This means that you can have your YAML file, your CloudFormation file, and a visual representation of that file in VS Code. Making changes in code, you'll see that represented in visual, and if you make changes visually, it is immediately reflected in the code at the side of that. Yeah? Oh. It is cool. Okay, fine. Yeah. But Q is also in there. Remember, Q sits inside VS Code as well. And you can ask Q questions about CloudFormation and then insert a response in it. And you can change your YAML file and the CloudFormation file and see this. And this multimodal way of question answer and diving deeper is something it's a really interesting new paradigm. I think that will help us as builders have a lot more fun in our world. Now, with all of that, you have one more day of learning ahead of you. I hope that I gave you a few hints today about being a good frugal architect, both in terms of cost as well as sustainability. And that if I can build MM models, you certainly can. I think there's never been a better time to be a builder. So you have one more day ahead of learning, tomorrow as well, a few more sessions. But tonight we're going to party. Yeah. Major Laser on the main stage, Portugal the Man on the live stage. Yeah. With all of that, now go build.
You're going to have to make a choice. Hit or stay.
Damn! What?
It's just so predictable.
So, what did I miss?
Nice keynote, Werner. But just one thing. You said I could scan my container images straight from my CI/CD pipeline. Yeah, I looked into it. Doesn't exist.
Maybe we just haven't launched it yet.
I knew it!
Ready, Werner? Do it.
3, 2, 1.
Now, go build.